If you've been following along my AI for Web Dev series, you've seen the soul-crushing experience that is CPU inference. Man, dude. And if you haven't seen any of that, well, you should check it out. I'll link it in the description below. It'll be perfect for your next binge. For today though, we're gonna put an end to that CPU misery and unlock the full power of GPU inference. So let's go ahead and dive into how to set up an AI or ML server from scratch in AWS. About my Intel Max compute performance. As much as I've tried, I'm not able to solder a 4090 to it. So the natural progression is either to build a new machine or to go the cloud route. And because building a new machine has a bit of an upfront investment and barrier to entry, I figured going the cloud route would be a bit more approachable for you all. You'll soon see why that was a comedy of errors on my part. So let's get a sneak peek of what we're gonna end up with. Our toolkit for today is pretty simple. We're just gonna need an EC2, we're gonna load Ubuntu on it, then some NVIDIA drivers and toolkits, and then lastly, Docker. And that's it. You may be thinking that of the cloud options, setting up an EC2 from scratch isn't really the easiest option. And you'd be right, it's not. There's things like Hugging Face endpoints that are for sure easier. But for us, we like pain and we like suffering, right? Not quite. Actually, we want this to be a portable setup. And generally speaking, the easier an option is, the more locked in you are. And we don't really want to be locked into a specific platform. You see, this setup, even though we're doing it on an EC2, could easily be applied to the gaming rig sitting under your desk, or a server sitting on the rack. So we need an EC2. No problem, right? It's not like there's hundreds of those to choose from. Let's narrow it down, shall we? We need a GPU. And speaking of GPUs, let's talk about vegetables. Imagine we want to chop up some vegetables. Bear with me. We could use a chef's knife. It's versatile, it's general purpose. We can do a lot of things with it, but typically you have to go from one thing to another thing in sequence. Or we could use a vegetable chopper. Nifty. It's great for chopping up vegetables. It's specialized. It can do one simple thing, but it can do it in parallel. See, it's got a lot of these little chopping cores. We might say it's got 2,560 of these chopping cores. And it can take these vegetables and chop them up in high throughput. Wonder where I could be going with this. So we've got our generalist, or we've got our specialist. Wonder which one will be better. Now, dear viewer, brace yourself. I was actually talking about CPUs or GPUs. You see, in practice, the hardware and design of GPUs for graphics also lends itself well to AI and ML workloads. Before we move on, there's just one other thing we have to cover. Some say it was a fateful night in Clarksdale, Mississippi, that Jensen Huang went down to the crossroads and at the stroke of midnight sold his soul to get CUDA. Others say it was created by a chap named Ian Buck. Probably the latter, but we'll never know for sure. In any case, CUDA is NVIDIA's not-so-secret weapon. Originally known as Compute Unified Device Architecture, CUDA is what allows us programmers to use NVIDIA GPUs for general programming. AMD also has ROCm. It's an open toolkit, but it's not quite as widely supported as CUDA. CUDA and ROCm is what allows us to use GPUs for accelerated computing. Okay, enough with the history lessons and back to AWS. I really wanted to do an AMD version of this, and if you'd like that, feel free to drop a comment down below. But you see, there's only one instance type in AWS, and it's got a paltry 8 gigs of VRAM. So, Team Green it is. The cheapest currently is a G4 DN X Large. It's got a T4 GPU with 16 gigs of VRAM, so that's pretty good. Not the newest, not the fastest, but it'll definitely get the job done. From there, we could step up to a G6 with an L4 GPU. It's newer, so it should have faster compute power, but it is a bit of a jump in price. Also, keep in mind, that as we're looking at these instance types, we really only care about the GPU. There's going to be a lot of them that just bump up the CPU and RAM, but not the GPU. For our OS, we're using Linux, naturally, and for our distro, we're going to use Ubuntu. I know it's not necessarily the most distinguished choice, but it's got a handy driver tool and it's got wide support. It'll definitely get the job done, but maybe later on we'll come back to Debian and reclaim some of our distro cred. Finally, we're coming to the part you've been waiting for. Let's go ahead and set up that EC2. Without further ado, let's go ahead and roll the tape. Let's go ahead and launch our instance. All right, let's call it something. Make sure to be extra creative. We're gonna pick Ubuntu because it's got that driver tool like we had talked about. The instance is going to be a G4DN X large, cheapest NVIDIA GPU with decent VRAM. Next, we're going to want to add our key pair that we imported. And we're going to want to allow all SSH 443 port 80 traffic from everywhere, just to make our lives easier for testing. For the persistent storage, we're going to start with 48 gigs, just because we're going to be pulling down Docker containers, pulling down models, etc., etc. And that should be everything. As a quick side note, this storage over here, this that comes with this instance type, is not persistent. So that's why we needed to add on some persistent storage. Let's do it. Oh, oof, that didn't quite go to plan, huh? Now, before you type skill issue or get good or noob, please know that this is a policy, not a tech issue. The problem at hand is quotas. Account quotas are limits placed on your account that specify what and how much of these services you can buy. Now, setting aside business strategy, there are some legit reasons for quotas, like limiting abuse from potentially malicious actors, preventing sticker shock from new users, and while it seems like AWS is infinite and all-encompassing, they're not quite there yet.
The more you buy, the more you save.
So they help with resource management and allocation. But we're not talking about 1,000 GPUs here to train the next llama. We're only talking about one. Okay, no luck on AWS, no problem. Maybe we can try Google. Well, actually, it's even worse there. You see, while AWS had a pretty clear error message and pretty clear next steps, Google just looks like it's failing, and it doesn't really tell you explicitly what's going on. You have to dig through and find out that it is, yet again, an account quota issue. I'm surprised to even be uttering these words, but let's see if Azure can come to the rescue. Well, spoiler alert, not so much. For one thing, even getting signed up is a challenge, and I know, skill issue, get good, but hear me out. It doesn't work in Firefox, and then when you open up a different browser, you go through a long stream of CAPTCHAs, 20 of them, and they're not very quick to do. And then when you finally get through that, you get taken to a page where it errors out, so then you have to reload in the browser yet again, and then you get taken to the portal, and then you have to go to a different splash page to pick a trial or another plan, and then when you finally get back in, you go to spin up an instance, and guess what? Surprise, surprise, you get hit with quotas again. So then you request an increase, and then that fails. So no luck with the big three, but there's got to be some other options, right? What about DigitalOcean? Not quite. Vulture? Nope. And maybe Linode, perhaps? You guessed it. Sales team. How about Google Colab? Well, that's a pretty cool tool, but it doesn't really give us access to the underlying compute. So what are we going to do? Well, let's go back to AWS and do the thing we've been dreading, contact customer support. Overall, in my case, it actually wasn't that bad. I just had to wait a couple days and then it was approved. Though, then again, being the huge YouTuber I am, of course, Amazon would roll out the red carpet for me. Your mileage may vary. Before we move on, do make sure that you have access to AWS and that you've got a quota increase on your account so you can spin up these G4DN instances. Assuming you've got that taken care of, let's go ahead and dive in. The first thing we're going to want to do is some housekeeping items. Most importantly, at least for me, is setting a budget. This will allow you to get alerts when you're getting close to whatever limits you want to specify. And again, we're trying not to blow a whole bunch of money on this. So you can see there's a billing and cost management service. I've got it open in another tab. Let's dive over there. And actually, the other way you could get to it is by searching for budget. So under billing cost management, we can see budgets. And then I already set up a monthly budget. I'll dive through that. You would do it through create budget. And then what we can see here is I don't want to spend more than $10. I know, really big spender here. And we're going to have a couple thresholds. So we've got $10 as our budget for the month. And then we're going to have alerts set up. So you can edit alerts. And what we want to do is when it hits a certain threshold, so 70% of forecasted, not actual usage, but it's predicting you're going to get that, send an email. 80% of when it actually uses that, so that'd be $8, send an email. And then lastly would be when we're at 100%. Again, I would really recommend setting up a budget just so that these things don't get away from you. The next thing that would be useful is setting up a key pair. Now, technically, you can have the EC2 create a key pair for you when it's provisioned, but for me, I already have a key pair set up, so I'd rather just use that. So you can search for this under key pair, right? Key pairs. And then there's going to be an action where in the drop-down it says import key pair. So from here, you could just copy your SSH key, import it. And then when you're creating an EC2, you can just reuse that key pair and it'll be really easy. Okay, the next thing I'm doing for this setup is automatically stopping any EC2s I have provisioned. Again, I'm just using this EC2 for experiments and things here and there. I don't need it running 24/7. Maybe that's useful for you too. There's a few ways we could do this. Amazon has a tool called Instance Scheduler, or Resource Scheduler, I should say, that is a little bit easier to get up and running. However, it assumes you want to stop and start, not just stop. So again, for me, I want to, whatever I have running, stop it and don't restart it, because I'll manually go in and start the instances if needed. Nonetheless, you can see Resource Manager, there's a help guide here on how you would start stop, and it's very easy. So you go under System Manager, you do quick setup, and then there's going to be a template for start stop. Under get started, and then it should be Resource Scheduler. Yeah. So then from here, you could specify what instances and what your schedule is. But again, start stop is assumed, not just stop. So that takes us on to the option we are going to go with, which is using a Lambda function in AWS to automatically stop all instances every night and not restart them. It's got a little bit more setup than just using the resource scheduler, but it is more flexible. So let's take a look at that. And this is the help article that I used. So you would go to your Lambda functions. You would create a new function. It's going to be pretty easy. You would just add code for the function, and I'll make sure that this is in GitHub and such. Basically, we're going to import the AWS library. Then we're going to have a handler. And all it's going to do is find all of our EC2s and then call the stop function or stop method. So for the EC2 library. So basically query for all of our EC2s and stop them. And that's it. Let's go ahead and test this. So I will spin up a instance. Micro instance should be sufficient. For this, let's just call it test. We can use AWS Linux because, we're just spinning something up to test this. So AWS T2 Micro defaults are fine. We'll use our key pair just for fun. And let's launch the instance. Okay, so if we go back to our instances, we'll give it a little bit just for it to get running. Click refresh like an impatient child. Not sponsored yet. And we can see now it is running. So this instance is running, and let's make sure our Lambda code works. So what we can do is, after we've put in our code function, we can hit test, and this will just create a test event. We don't actually need to pass any params to it. We'll leave it as is, but our Lambda function's not going to use any of this. And if we go ahead and hit invoke, we can see it is testing, and okay, and the response was stopped all instances. Now if we go back over to our instances tab and refresh it, we can see it stopped. So the benefit of this is, if you've got one of these beefy GPU instances, then you can spin it up, and then if you forget about it, this will stop it so that you're not getting charged for it. With AWS, you are charged when it's running, and you're charged for the storage continually, but you're not charged for the instance if it's stopped. So that takes care of some of our housekeeping items. So there is one last thing to do with the Lambda function. Right now it's able to run, but we had to trigger it manually, and that's not going to fly. So we need to set up a schedule. That's where EventBridge comes in. So if you look on the left here, there's going to be a scheduler subgroup. We'll go ahead and click on that, and then we're going to set up a schedule. I've already done this, so we'll go ahead and dive in here and edit it. It would be like you were creating it for the first time. So stop EC2 is the name. Then we're going to use a cron-based schedule, so it's going to run at midnight every day. And you can see some of the examples here. The flexible window is basically, it's going to say within 15 minutes it will run, not exactly at midnight, but within 15 minutes. That's fine for me. I think more than anything, it's helping Amazon kind of load balance. But you know, I'll be nice and benevolent. And we don't really need to worry so much about daylight savings, so we'll go next. Now we're going to select our target. So when a schedule runs, it's going to do something with that. In our case, we're going to invoke Lambda, and we're going to invoke our stop EC2 Lambda function. And again, we don't really need to send a payload. We just need to trigger it and enable. And retry, we'll leave it as the default so that if for whatever reason it fails, it'll try it again. And it's we're going to use a role that has access to start and stop EC2s. This is actually documented in their help, that this goes through setting up the role and such. And that's it. So now, every day at midnight, give or take, this should run and shut down any of the EC2s that, if I had forgotten to stop them, was running. Again, your mileage may vary. You might not need to do this or want to do this, but in my case, I want to make sure that I'm not racking up that huge bill. And that's how I would do it. And let's go ahead and get rid of this instance. Okay, so clean slate. We have our budget, we have a key pair, and now we've just got an account set up where it'll shut down instances so we're not racking up a huge bill. Let's go ahead and spin up a real EC2 that we want to work with. All right, so we're going to launch an instance. First step, we're gonna do it by hand, and then later on we'll do some refinements. So GPU test 1, let Ubuntu, like we said. This time we're using 24.04, x86, not ARM, and instance type. So again, we're doing g4dn.xlarge. This will have that T4. We're going to use our key pair. And then for demo purposes, we are basically just going to allow all traffic. Production-wise, you wouldn't want to do this. I mean, you probably wouldn't want to do this, but for demo purposes, since this will be short-lived, let's open it up. Next, we are going to bump up the storage. So 50 gigs, that's going to allow us to download packages. That's going to allow us to download Docker images. That's just going to allow us to download the models too. So 50 gigs should be enough for initial testing. You can always upsize later on, but 50 gigs is a pretty good starting point, and it's not too much more expensive than, really trying to optimize down to 31 gigs or something like that. It's kind of a pain if you have to keep upsizing because there are throttles on that. So 50 gigs. And I mentioned this before, I believe, but this instance, the G4 xlarge instance, does have its own storage, but this is not persistent storage. So between start-stops, anything that's in the non-persistent storage gets wiped out, which is why we're going to be bumping up the root storage. And with that, we should be good to go. Let's launch it. Okay, so our instance is being provisioned, and we can go back and it's running. Very exciting. Let's go ahead and connect to it, and let's go ahead and configure it first by hand and then a little bit slick down the road. All right, so the default username for Ubuntu is just Ubuntu. Again, for production, make sure to change this. Don't do root, all other legalese, lawyery, CYA type stuff. But we're logged in, but we have a lot of config to do. So I'm gonna set some environment variables, or instance variables, I should say, just as I'm copy and pasting from my notes. It'll make my life a little bit easier. So home dir, project dir for our test code. What model we're gonna use is, just for demo's sake, we're gonna use 5.3.1 mini 4K context, and specifically it's and another version of it that's been requanted with a more recent Llama C++ version. The official Microsoft one, at least last I checked, it was quantized a while ago. So with the latest Llama C++, it didn't seem to work well, but this one does work well, so shout out. So we're setting that instance variable. And then we're gonna set our project dir path. So it's basically our home dir plus our project dir. Again, we could use home, but this is copied from notes, which is why we're saying it explicitly. And then lastly, we're gonna set our Ubuntu version. This is when we get into NVIDIA, they have different versions for different releases. All right, let's install some basic packages. So we're gonna do apt-get update. The reason why we're using apt-get and not just apt is because apt-get is supposed to be more stable and it's better fit for, scripts and stuff like that. Apt by itself is more meant for interactive usage. So apt-get is generally better for automations. So just running update, and then we're going to do curl and some other packages that we'll be using later on for installing stuff. Now let's install Docker. Buyer beware, we're installing the Ubuntu version of Docker, in the sense that this is not installing from Docker their own package registry, right? We haven't gone through and added it. We're just running whatever's in the default Ubuntu package registries. So technically, to get the latest and greatest, you would go through, read the Docker instructions, read how to add their own repository, and install it that way. For demo purposes, this is more than sufficient. But buyer beware. Okay, so that's Docker. All right, next, we're going to use Docker Compose, but we need to add that plugin. So what we can do is, this is the documentation for it. You can see this is how we're going to go about installing it. Basically, you download it, make it executable, etc., etc. So we're going to need to, okay, so our Docker plugins are going to be there. And then we are going to make a directory for that. So we're making a directory for CLI plugins. Then we are going to download the plugin from their releases. So we're curling it, and then we're outputting it to that plugins directory, and then a plugin named Docker Compose. Then once that's done, we're just going to make it executable. All right, and now if we do sudo docker compose, well, we could do sudo docker because we did install, let's see, and cool, okay. And then how about compose sh, yep, that's all good. Chugging right along. Next, we are going to install the Ubuntu drivers tools. Now, the NVIDIA drivers, at least at the moment, are proprietary. Given that Linux is open source, with certain distros, Debian comes to mind. There's some special instructions on how to install the drivers, and they're not really a fan, understandably so, of, proprietary drivers. On Ubuntu, there is a driver tool that's available that makes it pretty easy. So that's what we're going to do right here. But we are going to install the driver tools. So in the order of how we install things matters. We have to do a couple reboots. So we'll do the drivers actually at the very end. So our driver tools are now set up. And next we are going to do the CUDA toolkit. So there is a decent amount in these steps. They're all pulled from NVIDIA's own documentation page. So let's do this. Install headers. Next, I don't know if we need to do this anymore, but we are going to delete an old repository. So this is just saying, this is the ID of it. It's not like there's some cryptic, this has to be known. Well, it does have to be known, but all it is just like the ID. It's like 1, 2, 3. So remove this old repo that's, 7FA to AF80, because there's a newer one now. And that's in the documentation. Okay, so next we need to do the keyring to be able to authenticate the packages. And this is where that Ubuntu version comes in. So it's going to be 2404 x86. All right, so we downloaded that. Now we need to install it. Okay. All right, so now with all of that, we should finally be able to install the CUDA toolkit. Let's run update since we did change some things. All right, and with any luck, we'll now be able to do apt-get install CUDA toolkit. Okay, so that should be CUDA installed. Next, we're going to want to install the container toolkit, which allows us to leverage the GPU within Docker. Again, these are the install instructions. We're gonna breeze through them a little bit. We are, again, gonna get some keys to be able to authenticate the packages. You can read through the syntax, but that's ostensibly what this line's doing. And then next, we're going to add that to the packages list. And now we're gonna run another update so it sees it. Next, let's go ahead and install the container toolkit. Okay. Last thing for the container toolkit is to configure it for Docker. Okay, actually configure Docker for it. All right, let's go ahead and restart Docker just to be on the safe side, because it says the daemon, it's recommended to restart it. Let's do that. Next up, for some of our app code, this is optional, but for some of our app code, we've been using OpenSearch, and this is something that we need to do, is the memory map limits. This is unrelated to Docker or CUDA or any of this other stuff. This is if you want to run OpenSearch for that RAG that we've been doing in the AI for Web Dev series. So optional step, but let's go ahead and do it while we're at it. And okay, so that's that. Just a few more things. Let's go ahead and install Make and C++ compiler, because we're going to compile llama C++ from source. All right, let's do a reboot just to be on the safe side, and then let's install the drivers, and that is going to be it for the basic setup. So we'll give it a second. These will be linked, of course. Let's see if it's rebooted. Okay. All right. Looks like we are good to go. So last thing we need to do is install the NVIDIA drivers themselves. I have found that using version 550 seems to work. Again, this is the T4 GPU on this instance, and this particular version seemed to work at the time. Maybe down the road, different version will work better. Maybe latest can work, but for now, I found that this particular version works, so we'll go with it. All right, drivers are installed. You guessed it, let's go ahead and reboot. Okay, all right, so in theory, drumroll please, if we did everything right, we should be able to check that the drivers are working. So we'll use the NVIDIA SMI tool. I think it's System Management Interface, if I'm not mistaken, or if I am, I'm sure. I'll check the comments. Let's see. All right, so SMI did seem to run correctly. So version 550, CUDA 12.4, and yeah, T4. All right, and there is the memory. So we're looking good. Okay, so on the host, we now have the drivers, we now have CUDA. We've got Docker, so we can run things natively with CUDA. But let's take a look and see, in theory, Docker should be able to leverage the GPU as well. So if we do Docker run with the GPUs, and we're going to run the Ubuntu image, and we're going to say the SMI command again, we should see actually pretty much the exact same thing. So it's going to pull the Ubuntu image, and yeah, there you go. Same exact thing, which is actually great news, because now we can take advantage of Docker to make packaging and orchestrating things easier, but we still get the performance benefits. So from here, we're at a really good baseline. Let's run some code just to confirm that it is in fact able to do what we want it to. To do that, we're going to deploy llama C++. So I have llama C++, the repo locally. So we are going to rsync it up to the server. So let's do that now. So if we take a look at deploy, very simple. All it's going to do is, again, just rsync the llama C++ directory, our Docker compose, run server, helper script. We'll look at that in a second, and then exclude everything else. We don't care about any of that other stuff. So if I do deploy, I need to update what server we're pointing to. So that was connect SSH client. This is the server. And now if I do deploy, this is done in the AWS environment file. So if I do aws.bin, yeah, that's just same stuff that the scripts are using. So now if I do deploy, it should rsync it up to the server. That's not true. I have to make sure our directories are set up. Let's go ahead and create those directories. So let's see if that's still in their project. If you recall just a minute ago, we created some instance variables. And because we rebooted, we'll want to reset those. Yeah, okay. Let's reset those. These mirror the variables from the environment file. All right, now let's go ahead and create our app code directory and stuff so we can rsync things to it. Okay, make dir models. That's where we're going to store things. Let's actually, while we're at it, let's go ahead and download the model from Hugging Face. It'll be quicker to go from Hugging Face to the instance than rsyncing it from my local. All right, so this is downloading the phi3 file, model weight file. Should only take a second actually. Okay, we're good. Are we good? Yeah, we're good. Now we can rsync it. So we deployed llama C++ from our local using that rsync script. You could check it out from GitHub directly, but again, for development purposes, we're going from local. So now if we take a look at our server, we have Docker Compose, we have llama C++, and we've got our run server. But there is something we need to do. So let's go ahead and llama C++. As you remember, we installed make and the C++ compiler. So we need to compile llama C++. So what we're going to do is make clean just to make sure there's no local copies. Next, we're just going to compile it. Because the T4 is an older instance or an older GPU, you do have to specify what CUDA version you're using. In our case, we're going to do 7.5. So that's what this is. And then also we're saying we do want to compile it with CUDA. So We're in llama C++, and let's go ahead and compile. Hey, huzzah. All right, we're all compiled. So let's put this away. And let's take a look. So we've compiled llama C++, and helps if you type right. So we're going to use the llama server binary. As I mentioned, we have a helper script to just fire things up. Let's take a look at that. And we'll look at it on local because I'm not sure if Vim is installed. Run server. Oh, it is. All right, pretty easy peasy. We're just specifying our model, the port, optionally limiting the context. And then again, it's just going to pass in some args. So let's invoke this llama server binary with this model file host 000. That's going to allow outside traffic, which port. We are going to offload the maximum number of layers possible to the GPU. Without this, it won't actually use the GPU. We're going to enable flash attention. That kind of helps with memory usage. And then lastly, we're going to use mlock, which is going to keep the model in memory. It's not going to, offload it or anything like that. So if we just do run server, fingers crossed, and need to do sudo run server because we're doing port 80. Sudo run server, come on. All right, making it hard for me. Or rather, my fingers are failing me. Sudo run server. Okay, now we are cooking. We should see in here, it's got the template, and we should see in here somewhere is like X number of layers offloaded to GPU. It might be lower down. So that's the template. Yeah, okay, 33 layers offloaded to GPU. Now, if we go to our browser and we take a look, instance, that's the IP. So if we do that, come on. HTTP, because we don't have a cert. Voila, llama C++ is running. Let's do a completion, 150 tokens. Okay, took a little bit. I think it was loading it up. So let's reset this and let's try this again. Okay, and now I think it's loaded into memory. You can see it's running pretty quickly. We have it compiled, we have it running natively, not in a container. We compiled from source. Let's refine this a little bit. We're going to do two things. We are going to kill this process, and we are going to run this in Docker. So let's take a look at our Docker file. It's pretty simple. You can see the documentation on GitHub for llama C++. This is the GitHub image repo. So we're going to use the server, specifically CUDA image. We're going to pass in pretty much our same command from our run server helper file. We're going to run on port 80. Internally, it's going to be port 8000. That can be whatever you want. We're going to volume map our model so it can access the model file. And then the only other thing we need to be on the lookout for is our resources. So this is what's telling Docker to allow the compose stack access to the GPU. You do need this, by the way. Without it, it won't work. All right, and if we do docker sudo up -- build, so what this is going to do is pull down the image. It's going to build it, and then it's going to run it. And in all honesty, it should look pretty much exactly like what we just did. So CUDA buffer, yep, all right, 33 layers offloaded. Let's see in the chat template. So now if we go back here, we can see, yeah, it looks pretty much exactly the same. We'll drop this down to, I think we had like 40 or 30 predictions. Let's change this prompt so it's a little bit more obvious. Let's do a completion and number of predictions and start. And yeah, you can see there, it came back right away. It's pretty performant, you know, not too bad. All right, let's stop that. So now we have a EC2 instance that can run Docker containers with the GPU. We've got the drivers installed. So even though we're using Gen AI for this, because we use the EC2, we could also do other machine learning accelerated compute. This is a pretty general purpose setup. And again, this is something that we could apply to your gaming rig or just a regular server. So this is pretty good. What's nice also is that we can start and stop this. The billing's predictable. Obviously, you know, there's going to be a certain cutoff point where if you're only doing a couple things, something like Bedrock or, you know, SageMaker or some of those other options will be cheaper. But the EC2 pricing is very predictable. And again, you can run whatever you want, traditional machine learning, Gen AI. That said, what we've done now is we've set up this server and it's kind of, you know, handcrafted. And that's not great. Because, you know, ultimately we don't want to be beholden to this server instance. So let's see if we can improve this a little bit. And that's going to be our last step. So let's go back to the EC2. And we are going to bid farewell to it, actually. I know, we went through all that trouble and now we're going to kill it off. But yes, we are going to do exactly that. We are going to go on this one. And it should be instance. Let's go back in here. Instance, state, where is it? GPU, and yeah, we're doing it. We spent all that trouble getting it set up and we're going to kill it, but for good reason. All right, so we're shutting down and terminating this instance. Now, again, we had some notes, a pseudo shell script we were walking through that made it pretty easy to set up. But let's see if we can actually get this down to a science. To do that, we're going to use a tool called Packer. So Packer is, you may have heard of it, it's similar to Ansible, but it's going to allow us to create an image. And then what that means is we can launch an instance from that image whenever we want. And we'll basically be jump started to the point of where we had the drivers and Docker and all that stuff set up and installed. So Ansible, on the other hand, it's gonna kind of be like a better shell script experience, right? Where it's still gonna run through all the steps, but it provides some retry capabilities and again, some configuration. So for our use case, Packer is the right tool. I'm assuming you have Packer set up. You can see the install instructions on their website, but let's go ahead and dive into our Packer file. So clear, and we're in our Packer directory on local. Let's take a look at our example Packer file. We're going to use the base Ubuntu image that will build off of it. We're looking for the canonical AMI owner, and we want the most recent. Next, we're going to SSH to it with the username Ubuntu, and we're going to allow timeouts of up to 5 minutes. Because we're doing drivers, we're going to need to reboot. So this just allows it to disconnect and try to reconnect without completely erroring out. Then what we want to do is, because we're building the image and we're going to be downloading things and downloading toolkits and stuff, we want a little bit more storage. Going back to our example, we did 50 gigs. That's not, again, strictly required, but it's a pretty good baseline. So we'll go ahead and use 50 gigs here as well for the root storage. Now we get into the build section of the Packer file, and this is going to be pretty much what we did previously by hand. So we're gonna install some packages, and then we're gonna install Docker, and then we're going to install Docker Compose. Then we're gonna do the driver tools. Then we're gonna do the CUDA toolkit. Then we are going to do the container toolkit. Then we're gonna up that memory map for OpenSearch. We're going to install make in G++ for C++ compilation. Then we're going to, at this point, we're going to reboot so that we can do the drivers and stuff like that. So this is a little bit funky, but basically we're running the reboot command. We're going to say expect it to disconnect and then wait for 10 seconds and then continue on. And that leaves us at the NVIDIA drivers. So we're loading up version 550. So again, this Packer file is essentially just those shell commands we ran, but defined out, and it's going to allow us to create an image from this. So let's try it out. You can use the format and validate tools to ensure that your Packer file is actually valid, but we've already done that. So I am going to go ahead and run this. And it should, if we go here, we're in EC2, we don't have any images just yet. We don't have any instances or images. So let's go ahead and build this. And it's going to take a while. So what Packer's doing under the hood is it's actually spinning up an instance. You can see that here. And it's going to run through all these steps, and then at the end it'll get us to kind of like a snapshot, and it'll store that as an image. And then from there, if we ever need to spin up a new EC2 with that configuration already done, it's a lot easier because we can just use our image. Okay. 20 minutes later, we're ready to go. Now, mind you, normally when you're building AMIs, you would do this asynchronously through CI or something like that. And again, the idea is, while it was slow, it's repeatable. And you're doing it once, and now you can spin up EC2s very quickly. And also, Packer can potentially target other deployments, right? Not just AWS. Let's take a look. So if we go back to our AWS console, we can see now we have our AMI in there. And if we take a look here, the temporary instance was terminated. So with any luck, I should be able to launch this, assuming I'm not at my quota limit. Let's see, GPU test 2. It's gonna use our AMI. We're gonna need to make sure to set the right instance type, G4DN, X large. We're gonna use our key pair. We're gonna use our network settings to allow all 50 gigs, because that's set from the instance. Let's launch it, fingers crossed. Okay, it is being provisioned. And if we take a look now, we have an instance running. Let's go ahead and connect to it. Interesting. I may have missed the 22 in the networking. Let's just double check. Event rules allow. Maybe it's not quite provisioned just yet. Yeah, I was getting a little eager. Permanently added. All right, and now let's see, NVIDIA. Hey, right off the bat, we're able to get to the GPU. So let's do one last test, and then I think we can go ahead and call it. So our last test is just to try running Docker and SMI. All right, and it ran in Docker. So now what we can do is we can spin up instances. We're not beholden to just that one instance we crafted manually. We can spin up instances. Maybe down the road we're spinning up multiple instances, and it's repeatable, and it's going to be a lot quicker. So that's Packer, that's AWS, and that's CUDA and Docker. I think for today, that's all I have for you. Thank you so much for watching, and we'll see you on the next one.